In this video, I'll explain the proof of Theorem 1 for the paper Uniqueness of DRS as a 2-operator resolvent-splitting and Impossibility of 3-operator resolvent-splitting. If you want to hear a usual talk where I explain the results at a high level without going into the details of the proof, you can watch my talk that I gave at the DMAX workshop on ADMM and proximal splitting methods and optimization that was hosted at Rutgers University by Professor Jonathan Eckstein. So first, let's go through the theorem statement and the rigorous definitions that define the statement of the theorem. First, we have a dimension D. This dimension D is finite, and we define the problem class 2op RD to be the collection of monotone inclusion problems of this form. So we are finding a zero of the monotone operator A plus B. Here, A and B, they're assumed to be maximal monotone operators on RD. We say a pair of functions t comma s is a fixed point encoding for 2op RD if, roughly speaking, a fixed point to the operator t corresponds to a solution to our original monotone inclusion problem. Rigorously speaking, we say t comma s is a fixed point encoding if we have this bidirectional implication, where a solution, if we have a solution to our monotone inclusion problem, then there is a z star, where z star is a fixed point of our fixed point mapping t, and the output of the solution mapping s is x star. Conversely speaking, if we have a fixed point of our operator, a fixed point mapping t, then the output of s is a solution to our monotone inclusion problem. So this definition is made to accommodate things like Douglas-Rachford splitting, DRS. In DRS, the fixed point iteration is defined via the usual z variables, but the z variables in most cases don't actually converge to the solution. It's the shadow iterates. It's the output x iterates that converge to the solution. So that is why we allow the fixed point mapping to have a different iterate or have a different z variable compared to the output to the solution mapping. We call T the fixed point mapping. T takes as input a monotone operator, in this case denoted A, another monotone operator, in this case denoted B, and an input vector of length d prime. And the output is of length d prime. The solution mapping takes in a monotone operator A, the monotone operator B, and it takes in an input vector of length d prime, and outputs a vector of length d. So notice that this d is the same d over here. D is the size of the original problem, and we allow d prime to be of a different length. Now, this may seem weird because if you're thinking of Douglas-Rachford splitting, the length of the z variable is the same as the length of the x variable, so in that case d prime will be equal to d. And when I define the notion of no lifting, we will immediately be assuming that d prime is equal to d. So for the purpose of Theorem 1, there is really no reason to allow d prime to be different from d. But when we talk about Theorem 4, we will allow d prime to be bigger than d, and that will actually correspond to using lifting. And that is why initially we allow d prime to be different from d. Theorem 1. I'll first state the theorem. I'll show you the theorem before I define the relevant words. Up to equivalence, T comma S is a frugal resolvent splitting without lifting for the problem class 2op RD, if and only if it is of this particular form, where alpha beta is positive, theta is non-zero, and eta is any real number. Now first let's look at this top part. So this part resembles DRS very much. And in fact, if beta is equal to alpha, then this number becomes 2, this number becomes 1, so we have the familiar 2x minus z. And when alpha is equal to beta, we have DRS. When alpha is not equal to beta, it's something else. Theta is assumed to be non-zero because if theta is equal to 0, then a fixed point mapping t just doesn't move at all, so it doesn't make any sense. And this S, this solution mapping, takes x1, x2, and it forms an affine combination of them, and the exact form of the affine combination is defined by eta, which is allowed to be any real number. Loosely speaking, we say T comma S is a resolvent splitting for the problem class 2op RD if it's a fixed point encoding constructed with resolvents of A and B, addition, and scalar multiplication. So when you evaluate T and S, the only operations that are, the only computational primitives that you're allowed to use are the resolvents of A, the resolvents of B. You can use addition, you can use scalar multiplication. Loosely speaking, we say T comma S is frugal if we use the resolvent with respect to A only once and the resolvent with respect to B only once. We say T comma S is without lifting, it uses no lifting, if the mapping T with operators A and B fixed is a mapping from RD to RD, and S is a mapping from RD to RD when A and B are fixed. In other words, T comma S is without lifting if D prime is equal to D. Now let's make the definitions precise. So first we'll write I to be the identity mapping, but it's the identity mapping that takes in not only the input vector, but it takes in the operators A and B. So I takes in an operator, a vector, and outputs a vector, and it basically ignores the input operator and just simply outputs the input vector. Next, we write J alpha 1 to be the resolvent with respect to the first operator. So J alpha 1 takes in an operator, a vector, and outputs a vector. And the action is that you take the resolvent with respect to the first operator, A. The second operator, B, is ignored. We define J beta 2 to be the resolvent with respect to the second operator. So the domain and the range are defined analogously, and the action of J beta 2 is to apply the resolvent J beta B with the input Z. The first operator A is ignored. Next, we define a class of mappings in a way analogous to how algebraic classes are constructed. So first we define F0 to be the class of mappings that contain the identity mapping, the resolvents with respect to the first operator, and the resolvents with respect to the second operator. I use the plural resolvents because here, this is the class of resolvents with respect to the first operator with any positive parameter alpha. So if we have a different alpha, related but different resolvent evaluation. Next, we recursively define Fi plus 1 as the class of mappings that are the sum, the quote-unquote composition, scalar multiplication. The composition, quote-unquote composition, is defined by fixing the operators A, B, and composing the output of the first operator, the output vector of the first operator to the input as the input vector of the second operator. So this is the composition you would have if you view A and B as sort of a fixed parameter for your problem. Note that because this gamma is allowed to be 1, our classes Fs are increasing classes. In other words, F0 is in F1 is in F2, so on and so forth. And finally, we define F to be the union of all such Fs. To clarify, the elements of F, they take as input an operator, and a vector, and it outputs a vector. So for example, if R is a member of F, and if A and B are maximal mountain operators, then R with A and B provided, and the input vector left as a variable, maps a vector to a vector. These mappings are constructed with finitely many resolvents of A and B, addition and scalar multiplication. Next, we say T comma S is a resolvent splitting without lifting for the problem class 2 app RD if TS is a fixed point encoding for the problem class 2 app RD and TS is in F. Remember that T in F, this implies that when you fix A comma B and leave the vector input as a variable, this maps from RD to RD. And I'm using the word resolvent splitting to imply two conditions. The first condition is that it's actually a fixed point encoding. It's not just some nonsense function. It actually encodes fixed points of the problem. And the second condition is that it actually only uses resolvents, scalar multiplication, and vector addition in its construction, in its computation. When T comma S is in F because of its finite construction, we can evaluate T and S for given input vector Z and given mountain operators A and B in finitely many steps. And each step is scalar multiplication, vector addition, or a resolvent evaluation. We say T comma S is frugal if it has a step-by-step, a serial evaluation procedure such that exactly one step computes the resolvent with respect to A and exactly one step computes the resolvent with respect to B. And both T and S, the outputs of T and S, are computed by the end. By the way, such evaluation procedure is not unique, and there could be some foolish evaluation procedures where you unnecessarily compute useless things, but we say T comma S is frugal if this good evaluation procedure exists. Given a fixed point iteration, we can scale it with a non-zero scalar to get another one that is essentially the same. So if we have the fixed point iteration zk plus 1 is equal to tzk, then we can multiply the output by a on both sides, and then scale the zk variable by a, and then compensate by a inverse inside. This will give us a different iteration, a quote-unquote different iteration, but conceptually there's nothing new here. It's essentially the same iteration. Given a resolvent splitting that requires two operators, we can swap the role of a and b to get another one, and indeed that would give us a iteration, but conceptually it's no different. If we have the fixed point encoding T comma S, where with the inputs A and B, if we swap the role of B and A, we get a different fixed point encoding. And we see this in Douglas-Rachford splitting. In Douglas-Rachford splitting, the roles of the operators A and B, they're not symmetric. One of it is evaluated before the other. And if you swap the ordering, it's not the same iteration, except in certain very special cases. Nevertheless, swapping the ordering of the operators doesn't really produce anything conceptually new. Therefore, we say two resolvent splittings without lifting are equivalent if one can be obtained from the other through scaling with a non-zero scalar or swapping the roles of A and B. Now that we've made the definitions rigorous, let's move on to the proof of Theorem 1. Let me state Theorem 1 again. Up to equivalence, T comma S is a frugal resolvent splitting without lifting for the problem class 2 op RD, if and only if it is of the form given by this theorem, where alpha and beta are positive, theta is non-zero, and eta is a real number. The proof in the backward direction is essentially the same proof as the proof that DRS is fixed point encoding. So the backward direction asserts that this splitting is indeed a fixed point encoding, and that one is the easier direction. It follows from standard mundane calculations, and the paper provides the proof in one paragraph. The main contribution of this theorem and the more difficult direction of this theorem is the forward direction. The forward direction states that any frugal resolvent splitting without lifting is equivalent to this form. That is the forward direction. That is the more difficult direction. Let's focus on that part. Consider an evaluation procedure T comma S that establishes frugality. So again, the assumption is that there is an evaluation procedure, a serial step-by-step ordering to the computation. And in that ordering, either the resolvent with respect to A or the resolvent with respect to B, one of the two are evaluated before the other. Without loss of generality, let's assume that the resolvent with respect to A is evaluated before the resolvent with respect to B, because otherwise we can consider the equivalent splitting that has T tilde comma S tilde that has the ordering of the operators A and B swapped. That will make resolvent with respect to A be evaluated first. Next, let's set up some notation. So we will consider the evaluation of T and S at some input vector Z0. By assumption, because the splitting is frugal, the resolvents with respect to A and B, they are evaluated, each evaluated exactly once. There is Z1 and Z2 that are the inputs to the resolvent evaluations, and there is X1 and X2, the outputs to these resolvent evaluations. In other words, we define X1 equals J alpha A Z1, and X2 equals J beta B Z2. Let's define A tilde X1 and B tilde X2 to be the outputs of the operator A and B. And they're defined implicitly through these two equations. And these definitions make it so that A tilde X1 is a member, is within A X1, and B tilde X2 is within B X2. All computational steps except the evaluations of the resolvents with respect to A and B amount to forming linear combinations of previous information, because scalar multiplication and vector addition, these are the only two other operations allowed in T comma S. So if you're not evaluating a resolvent, then you're performing scalar multiplication and performing vector addition. That is the definition of a linear combination. Now that we have these definitions set up, we can express the evaluation of T and S at the input vector Z0 via this linear system. These star symbols represent fixed scalar coefficients that we have not yet parameterized. We will simplify this linear system a little bit, and then we will parameterize in order to make the notation tractable. This is represented as a matrix vector multiplication. So this is our matrix, this is our vector. Now, each scalar block within the matrix is to be understood as a d by d subblock. So this is the d by d zero matrix. This is the identity matrix. This is this scalar multiplied by the d by d identity matrix. This is alpha times identity, the d by d identity matrix. Because z0, z1, x1, remember these are vectors of length d. z1 gets multiplied to unknown scalar times identity. z1 gets multiplied by identity, and those two added is equal to 0. Now let me explain the meaning of each row line by line. The first row defines z1, and z1 again is the input to our first resolvent evaluation. z0 times something, and then z1 times 1, and those two added is equal to 0. So this definition provides z1 is some scalar multiple of z0. In other words, we can write z1 is something times z0. That's the meaning of this first row. Next, we have row 2, which represents our first resolvent evaluation. Our resolvent evaluation leads to this monotone inclusion, and that's what's expressed in this second row. We can express this second row equivalently as minus z1 plus x1 plus alpha a tilde x1 is equal to 0. This is the meaning of our second row, and this corresponds to this monotone inclusion. Row 3 defines z2, which is the input to our second resolvent evaluation. If we write out the meaning of this row explicitly, we get z2 plus star x1 plus something z1 plus something z0 equals 0. This is the meaning of row 2. It defines what z2 is. Row 4 represents the second resolvent evaluation, which leads to this monotone inclusion. This monotone inclusion is what's represented in row number 4. Row 5 defines the output of the fixed point mapping T, so it corresponds to TZ0. If we count column 1, 2, 3, 4, 5, 6, so this 1 is on the 6th column, and component 1, 2, 3, 4, 5, 6, so the 6th component is here. So TZ0 gets multiplied by 1, and therefore row 5 can be understood as TZ0 plus something something plus dot 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 something something equals 0. That corresponds to row 5. TZ0 is expressed as a linear combination of everything else. Row 6 defines the output of the solution mapping SZ0. This 1 is multiplied to SZ, and we have SZ0 plus something something dot 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 plus something something equals 0. That corresponds to row number 6. Next, we want to simplify the system, so we will permute some rows. This permutation corresponds to left multiplication by this invertible matrix. So this is a square matrix, and it's a permutation matrix, and therefore it's an invertible matrix. We initially had this linear system. We left multiply by that matrix, and we get this linear system. The two linear systems are equivalent because they correspond to left multiplication by an invertible matrix, which is a reversible process. In the step-by-step evaluation procedure of t, s, either t is evaluated before s or s is evaluated before t. As our first case, consider the case where s is evaluated before t. In this case, the evaluation of s does not depend on the output of the evaluation of t. And this structure is reflected in this linear system through this 0. The last row defines the output of s, and s is defined as a linear combination of the previous information. And in this linear combination, there is no contribution of the output of t because s is evaluated before t. To simplify the system further, we perform Gaussian elimination. Pay attention to this 0. Previously, a non-zero occupied that position. To eliminate that non-zero, we take this last row, multiply a scalar, and subtract it from this row. Because we have a 0 here, this component is unaffected by that process. And by the way, these components can be affected by this process. This corresponds to left multiplication by this invertible matrix. As an aside, one way to immediately see that this matrix is invertible is to note that the diagonals are non-zero and that the matrix is upper triangular. Next, let's consider the second case, where the evaluation of t completes before the evaluation of s in our evaluation procedure. In this case, the evaluation of t, defined through this row, does not depend on the output of S, and that is reflected by this 0. T is defined by this row as a linear combination of all previous information, and in this linear combination, there is no contribution from the output of S. Again, to simplify the system, we perform Gaussian elimination. Pay attention to this 0. Previously, that position was occupied by an unspecified scalar. To eliminate this non-zero, we take this row, multiply it by an appropriate scalar, and then subtract from this row. By the way, because this component is a 0, this component is unaffected by this operation, and these components can be affected by these unspecified scalars. Again, this corresponds to left's multiplication by this invertible matrix, and we know it is invertible because the diagonals are non-zero and it is lower triangular. We considered the two cases, and regardless of which case we started from, we arrived at the same exact linear system. Let's continue to perform Gaussian elimination to further simplify the system. We take this row, multiply by a scalar, and subtract from this row in order to cancel out the non-zero over here. We take this row, multiply by a scalar, and subtract from this row to cancel out this non-zero. This operation corresponds to left multiplication by this invertible matrix. Let's continue. We take this row, multiply by a scalar, subtract from this row to cancel out this non-zero. We take this row, multiply by a scalar, and subtract to cancel out the non-zero. This corresponds to left multiplication by this invertible matrix. Next, we take this row, multiply by a scalar, and subtract from this row to cancel out this non-zero. Again, we take the same row, we multiply by a scalar, subtract from this row to cancel out this non-zero. This corresponds to left multiplication by this invertible matrix. Next, we take this row, multiply by a scalar, and subtract from this row to eliminate this non-zero. We multiply by a scalar and subtract from this row to eliminate this non-zero. And we multiply by a scalar and subtract from this row to eliminate this non-zero. This operation corresponds to the left multiplication by this invertible matrix.
Let's start to explicitly parameterize the unspecified parameters one at a time. We parameterize the coefficient on the top left corner as minus a. The role of minus a is to define z1 equal to a z0. In other words, the evaluation of t comma s starts with the evaluation of j alpha a at the input a times z0. If a is equal to 0, then the resolvent evaluation ignores the input z0 and always uses 0 as the input. Since t comma s accesses the operator a only through the evaluation of its resolvent, it should not be possible for t comma s to evaluate the resolvent of a only at 0 and still somehow encode the zeros of a plus b. The zeros of a plus b could be anywhere. Let's make this argument formal. To prove a not equals 0, we assume a equals 0 for contradiction. Let a be the single-valued operator of this form. C1, using this definition, is positive in order to ensure a is monotone. Since the output of a at the input 0 is 0, in other words, 0 equals a0, the resolvent with respect to a evaluated at 0 outputs 0. Let b be the single-valued operator of this form. C2, using this definition, is assumed to be a non-zero d-dimensional vector. Since the output of the resolvent with respect to a at 0 is equal to 0, regardless of the value of C1, the mappings T and S are independent of the value of C1. The set of fixed points of T and the set of outputs of the solution mapping S evaluated at a fixed point do not depend on the value of C1. However, the solution of the monotone inclusion problem defined by A and B, in other words, the 0 of A plus B, does depend on C1. Since T comma S is assumed to be a fixed point encoding, T must have a fixed point Z star, and the output of the solution mapping at Z star must be the solution. This is a contradiction, and we are forced to conclude that A is equal to 0. Now we know A is not equal to 0. We left multiply our linear system by this matrix. This matrix is invertible because all the diagonals, including the A, are non-zero. The multiplication results in this linear system. We explicitly parameterize this non-zero to be equal to minus A, and the left multiplication makes this entry equal to A. That linear system is in turn equivalent to this linear system. Pay attention to these two entries. The A that used to be over here is now transferred to this location. This moving of the constant A would also affect these non-zeros as well. The A that used to be over here is transferred to this location. Then we multiply A inverse A, which is equal to 1, and we will multiply A inverse A, which is equal to 1.
By redefining t comma s to be the equivalent scale splitting, we get the equivalent system that looks like this. Now there is no a in z0, the fixed point mapping t, and the solution mapping s. We now explicitly parameterize the 8 remaining parameters as theta 1 up to theta 8. We have theta 1, theta 2, theta 3, theta 4, theta 5, 6, 7, 8. This system defines t comma s. In other words, it specifies the evaluation of t comma s at any point z0. Of course, x1, x2, and the output of the solution mapping sz0 need not be solutions of the monotone inclusion problem because the input z0 is arbitrary. To summarize our progress, we have shown that any frugal resolvent splitting without lifting can be expressed in this form.
Let's take a moment to consider what happens with Douglas-Rachford splitting. This will illuminate the direction this proof is headed in. Under this formulation, DRS has this form. Let me explain each row line by line. Row 1 defines z1 equals to z0, where z1 is the input to the resolvent with respect to A. Row 4 corresponds to the evaluation of the resolvent with respect to A. Row 2 defines z2 equals 2x1 minus z0, where z2 is the input to the resolvent with respect to B. Row 5 corresponds to the evaluation of the resolvent with respect to B. Row 3 defines the output of the fixed point operator as z0 plus theta times x2 minus x1. Row 6 defines the output of the solution mapping S as an affine combination of x2 and x1. This linear system represents the evaluation of t comma s at any arbitrary input z0. In other words, this system defines t comma s. To establish that DRS is a fixed point encoding, one shows that x1 is equal to x2, and that is equal to the output of the solution mapping S, and furthermore, the output of the operators a tilde x1 and b tilde x2 sum to 0. We add an additional row representing the fixed point condition z0 equals tz0. Now the system represents evaluations of t comma s at fixed points. We take this linear system and left multiply by this vector. This left multiplication combines these two rows, and that gives us this linear equality, which is equivalent to x1 equals x2. We take the linear system and left multiply by this vector, which combines these three rows, and that gives us this linear equality, which is equivalent to the output of the solution mapping is equal to x1. We take the linear system and left multiply by this vector. That gives us this linear equality, which is equivalent to 0 equals a tilde x1 plus b tilde x2. With DRS, it is possible to perform Gaussian elimination with the linear equalities defining t comma s and the fixed point condition tz0 equals z0 in order to conclude x1 equals x2, and that is equal to the output of the solution mapping, and that the output of the operators a and b sum to 0. With other fixed point encodings, should we not be able to do the same? How else could the fact that z0 is a fixed point certify that the output of the solution mapping is a solution to the monotone inclusion problem? This turns out to be true. We must be able to establish x1 equals x2, x1 equals to the output of the solution mapping S, and the output of the operator sum to 0 through the linear equalities, as otherwise we can construct counterexamples that contradict the assumption that t comma s is a fixed point encoding. Consider the linear system equalities with the fixed point condition tz0 equals z0 added as this row. We will label this linear system of equations as equation number 1. We call this matrix matrix M, and we call this vector, the vector of variables, vector v. Before we proceed, let me quickly tell you about this lemma. Let M, an m by n matrix, and C, a length n vector, represent fixed coefficients. Let V represent a vector of n variables. If there is a W, a length m vector such that W transpose M is equal to C transpose. In other words, if we can write C transpose as a linear combination of the rows of M, then the linear equalities MV equals 0 imply the linear equality C transpose V equals 0. If there is no such W, in other words, if C transpose cannot be represented as a linear combination of the rows of M, then there is an instance of the variable vector such that MV is equal to 0, but C transpose V is not equal to 0. Another way to state this lemma is to say that the system of linear equalities MV equals 0 implies the linear equality C transpose V equals 0 if and only if C transpose can be represented as a linear combination of the rows of M. Let's assume for contradiction that our linear system number 1 this linear system, does not imply the linear equality x1 equals x2. By the lemma, this means that there is a specific instance of the variable vector such that mv prime is equal to 0, but x1 prime is not equal to x2 prime. The vector v prime represents an evaluation of t comma s at a fixed point for any maximal monotone operators a, b, such that operator a outputs a tilde x1 prime at x1 prime, and operator b outputs b tilde x2 prime at x2 prime. The evaluation is as a fixed point since we enforced the fixed point condition in our linear system number 1. Let A be the single-valued operator of this form, and let B be the single-valued operator of this form. Note that A and B are designed so that the output of A at x1 prime is equal to A tilde x1 prime, and the output of B at x2 prime is equal to B tilde x2 prime. Write x star for the output of the solution mapping S. Since t comma s is a fixed point encoding, we have 0 equals A plus B x star. In other words, x star is a solution to the monotone inclusion problem defined by A and B. However, x1 prime and x2 prime are not equal. Therefore, either x1 prime is not equal to x star, or x2 prime is not equal to x star, or both is also a possibility. Without loss of generality, we assume x1 prime is not equal to x star. Loosely speaking, x1 not equals to x star means t comma s was able to identify that x star is a solution without even examining the output of A at x star. The evaluation of t comma s depends on the operator A only through the output at x1 prime. If t comma s is not examining the operator A at x star, what prevents us from changing the value of the operator at x star? Let's make a formal argument. Define C to be the single-valued operator of this form. Remember, A was defined to be of this form, and C is defined similarly except that we have a 2 here. As it was the case for A, the operator C is defined so that the output at x1 prime is equal to A tilde x1 prime. Because the output of the operators A and C are the same at x1 prime, changing the operator from A to C does not affect the evaluation of T and S. However, x star is no longer a solution to the monotone inclusion problem defined by C and B, because the output of the operators C and A are not the same at x star. In other words, for operators C and B, z0 prime is a fixed point of T, but the output of the solution mapping S is not a solution. Therefore, T comma S fails to be a fixed point encoding for the maximal monotone operators C and B, and we have a contradiction. This proves that this system of linear equalities does imply the linear equality x1 equals x2. Next, assume for contradiction that our linear system of equalities 1 does not imply the linear equality SZ0 equals x1. By the lemma, this means that there is a specific instance v prime of this form, such that mv prime is equal to 0, but the output of S is not equal to x1 prime. By the way, we have established that x1 prime is equal to x2 prime. Again, loosely speaking, the output of S not being equal to x1 prime means t comma s was able to identify that the output of S is a solution without even examining the output of the operator A at the purported solution. We draw a contradiction by changing the operator value at the purported solution. Using the same definition of operators A, B, and C, the same arguments carry over, and we can establish that changing the operator A to operator C does not affect the evaluation of T and S. So Z0 is still a fixed point, and the output of the solution mapping S should still be a solution. Let's write x star for the output of the solution mapping S. Since we assumed, for contradiction, that x star is not equal to x1 prime, we have that the output of A plus B and C plus B are not the same at x star. Remember that A, B, and C are single-valued. So it is not possible for both the left-hand side and the right-hand side to be equal. Therefore, T comma S fails to be a fixed point encoding for the maximal monotone operators A and B, or the maximal monotone operators C and B. This is a contradiction, and the contradiction forces us to conclude that the linear system of equalities 1 does imply the linear equality SZ0 is equal to x1. Finally, assume for contradiction that our linear system of equalities 1 does not imply the linear equality A tilde x1 plus B tilde x2 equals 0. By the lemma, this means that there is a specific instance v prime of this form, such that mv prime is equal to 0, but A tilde x1 prime plus B tilde x2 prime does not equal to 0. Loosely speaking, A tilde x1 prime and B tilde x1 prime not summing to 0 means T comma S was able to identify that the output of the solution mapping is a solution without obtaining outputs of operators A and B that sum to 0. This cannot work if A and B are single valued. Remember, we now know that x1 prime is equal to x2 prime and that that is equal to the output of the solution mapping S. Define A and B to be the single valued operators of these forms. Again, note that A is designed so that the output at x1 prime is equal to A tilde x1 prime, and B is designed so that the output at x2 prime is equal to B tilde x2 prime. Then, z0 prime is a fixed point, but the output of A plus B at the purported solution is A tilde x1 prime plus B tilde x2 prime, which is not equal to 0. Therefore, T comma S fails to be a fixed point encoding for these maximal monotone operators A and B, and we have a contradiction. This contradiction forces us to conclude that the linear system of equalities 1 does imply the linear equality A tilde x1 plus B tilde x2 equals 0. With these assertions proved, we proceed to complete the proof. We take this linear system of equalities and left multiply it by this invertible matrix to obtain this linear system. This operation affected these coefficients. Because the system of linear equalities must imply x1 equals x2, and because of where the zeros and non-zeros are placed in this linear system, we have to conclude that theta 3 is equal to minus 1, theta 4 is equal to minus theta 5, and that is equal to some non-zero theta. Let's further spell out this argument. The linear equality x1 equals x2 can be expressed with this linear system. This minus 1 gets multiplied to this x1, this 1 gets multiplied to this x2. By the lemma, the system of linear equalities 1 implies this current equality if and only if we can linearly combine the rows of our system of linear equalities to obtain this equality. Note that these components are 0, and these two are the only non-zero components in this linear equality. This is our system of linear equalities. Row 7 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 9th column. Row 6 cannot be used in this linear combination, as any non-zero contribution will place a non-zero component on the 8th column. Row 5 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component in the 7th column. Row 4 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 6th column. Row 2 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 4th column. Row 1 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 2nd column. This leaves us with only this row to imply this linear equality. For this implication to be possible, we need this component to be equal to 0. In other words, we need theta 3 to be equal to minus 1. And we need these two components to have the same non-zero magnitude, but of opposite signs. In other words, theta 4 must be equal to minus theta 5, and that must be equal to some value theta that is not equal to 0. Plugging this into our linear system, we get this simplified linear system. Because this linear system of equalities must imply that the output of the solution mapping must be equal to x1, and because of where the zeros and non-zeros are placed, we have to conclude that theta 6, theta 7, and theta 8 must be of this form. Let's further spell out this argument. The linear equality SZ0 equals x1 can be expressed in this form, where this minus 1 is multiplied to x1, and this 1 is multiplied to SZ0. By the lemma, the linear system of equalities 1 implies this equality if and only if we can linearly combine the rows of our system of linear equalities to obtain this equality. Row 6 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 8th column. Row 5 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 7th column. Row 4 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 6th column. Row 2 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 4th column. Row 1 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 2nd column. This leaves us with these two rows to imply this linear equality. For this to be possible, this component has to be equal to 0. In other words, theta 6 must be equal to 0. Note that this 1 is matched with this 1. To be able to multiply this row by a scalar and add to these components to obtain minus 1 and 0, theta 7 must be equal to minus 1 plus eta, theta 8 must be equal to minus eta for some eta. We plug these conclusions in to get this simpler linear system of equalities. Because the system of linear equalities must imply that the output of the operators A and B must sum to 0, and because of where the zeros and non-zeros are placed, we will have to conclude that theta 1 is of this form and theta 2 is of this form. Let's further spell out this argument. The linear equality 0 equals a tilde x1 plus b tilde x2 can be expressed as this linear equality, where this one is multiplied to a tilde x1 and this one is multiplied to b tilde x2. By the lemma, the linear system of equalities implies this current equality if and only if we can linearly combine the rows of our system of linear equalities to get this linear equality. We left multiply our linear system by this invertible matrix to obtain this linear system. By the way, it is straightforward to verify that the determinant of this matrix is 1 over theta, which is non-zero, and therefore that this matrix is invertible. Next, we left multiply our system by this invertible permutation matrix to obtain this linear system. Remember, the goal is to combine the rows of this linear system to obtain this linear equality, which has non-zeros only in these two positions. Row 7 cannot be used in this linear combination, as any non-zero contribution will place a non-zero component in the 9th column. Row 6 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component in the 6th column. Row 5 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 5th column. Row 4 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component on the 4th column. Row 3 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component in this 3rd column. Row 2 cannot be used in the linear combination, as any non-zero contribution will place a non-zero component in the 2nd column. This leaves us with this row to imply this linear equality. For this implication to be possible, we need this component to be equal to 0 and these components to have equal value. This corresponds to this conclusion. Finally, we plug in these parameters and express the splitting in a functional form rather than as a linear system, and we get the splitting of Theorem 1. This completes the proof.